Oh. Duh. This is how fast the prime frame is moving relative to the initial frame. That's V there. There we go. That's V. That looks like a W now. V times V. So this is U over gamma 1 minus beta squared. And 1 over gamma, let's try this. Gamma times 1 minus beta squared is 1 over the square root of 1 minus beta squared times 1 minus beta squared, which is the square root of 1 minus beta squared, which is 1 over gamma. Therefore, this becomes gamma U. And so now we have mass m naught squared minus beta squared gamma. Oh, okay. So m naught squared over m squared equals u naught prime over u. It's 1 over gamma. Based on this. U over u prime is 1 over gamma. Now it's a matter of getting to the form that we like. I'm just going to bring gamma, I'm going to get rid of the fraction b's, bring gamma squared up, bring m squared up. So we'll get gamma squared m naught squared is equal to m squared. Take the square root. And we have mass is equal to gamma times epsilon naught. So at least part of the reason for doing this is just to show manipulation of the equations that we've been working with here in a slightly more formal setting. And then refer back to notes for equals MC squared once you have that. Actually, the other proofs of this relationship start with E equals MC squared and then work backwards. Besides the 3 minimum approaches. Questions? I can see people are enthralled. Why don't we take a break, come back, and then I'll hopefully teach you a little bit more to question everything you've ever thought you knew.
Well, so I went through this to figure out how long that is right there. And that's 4,000 years.
Okay. So what we've basically been learning up till now is classical physics, relativity. Sometimes it's usually here referred to as semi-classical. It basically adds one restriction into it. But there are problems with almost everything that you've learned, and does not invalidate anything that you've learned. But at some point, it seems to break down. So if I take a black box and I heat it up, this is my flames to heat it up. It's a box and not just a cube. It's hollow inside. There's basically a cavity inside. And because it's black, it's going to absorb as close as we can get to absorbing everything. You put a little hole in it so that some of the radiation inside will come out. And so they looked at the temperatures of it, so the temperature and what radiation was coming out of it, and they did a plot. So if we're looking at the intensity of the energy coming out versus the frequency, the classical prediction is that it should do something like this, using classical thermodynamics. And what they saw was something like that. Now, obviously, there's a difference between these two. So, like, one of the big questions is, why is there this gap here? So, the first step in this venture was that a guy named Max Planck just did I've got the data here, let's see if I can come up with an equation just by, probably a certain amount of trial and error, but a certain amount of experience also, trying to find some graph that matches that. And he came up with that the intensity, he comes up with this equation. C, speed of light, lambda is the wavelength of light that's coming out. K is Boltzmann's constant, T is temperature, and H was something that he needed, and it is 6.6. Thank you. Going back and forth between 2 and 3 times 10 to the negative 34th joule seconds. I'm going to go with that for right now until I find otherwise. This is now known as Planck's constant, or Planck's constant, probably closer to it. Now, when he first started doing this, he had no idea why this worked. So he sort of came in at sort of the back door there. He came up with the equation first, published it, and then spent trying to figure out how do you actually get to this. And eventually realized that this works if you assume that energy just can't be anything, that energy has very discrete levels. Energy is discrete. In other words, since it's not a spectrum, as in, it's not every number in between A and B. Let's go ahead and mix metaphors there. It's only in certain values in between there, and what basically is energy is quantized. So this was one of those questions, and obviously I've condensed the story down into a much shorter tale. Get back to my cheat sheet. Another issue in classical mechanics that I couldn't quite explain was the photoelectric effect. So this is known as black body radiation. And then there's the photoelectric effect. So one of the big questions early on in, going back to Newton, I guess we should say, is whether light was a wave or a particle. Newton was of the firm belief that it was a particle. One of his rivals, Huygens, said it was a wave, and they both came up with theories. If you might be able to pull this off. All right, can you see? You can't really see a stream of light coming in from the window, can we? It's sort of on my arm right there. Sort of. So Newton said is light's a particle, it comes through the window and you can clearly see there's shadow and there's not shadow. And the wave people said, yeah, but right along the edge it's really not as clear cut as you're claiming. And the particle people say, well, that's just because some things just bounce randomly. They hit part of the window and bounce off. And so that was late 1600s. Early 1800s, there was an experiment where they finally had the technology they showed the light through what's a double slit, known as the double slit experiment. If it's a particle, then what you would expect to see is a whole bunch of light hitting there and a bunch of light hitting there. If it's a wave, what you would expect to see, well, just imagine you have these water waves coming in, and they hit these two gaps in the wall. Whatever comes through is then going to start spreading out. And you get these points here where the waves overlap and you get constructive interference. And you have point right here where you have destructive interference, where one is troughing while the other one is peaking. So what you would expect is a whole bunch of series of constructive and destructive interference, and so you'd get a lot of light here, not as much there, a little less. And it sort of peters off as you get farther away from the central axis. And so in the experiment, they did it and they got this. So it seemed very clearly light was a wave. The trouble is, not all the evidence supported that. So you take something that I always picture metals when they do this, because metals have usually electrons that easily move. And you basically shine light at the surface. Now, if you shine light at it, sometimes an electron gets enough energy, it hits the electron, the electron then goes shooting off. You can have a detector here, and you can start to see that electrons are moving. You have a change in, you have a potential difference, you have a current, however you want to word it. The trouble is, not all light was able to eject the electrons. There's a threshold. I can't remember, it seems like threshold was one of those words that's misspelled, but 2 H's or 1? One, okay. So there's a threshold energy. Now, if I shine the light at it, no electrons are coming off. I've obviously not hit that threshold, but if it's a wave, I can easily increase the amount of energy just by increasing the amplitude. Or in the case of light, make it brighter. Time 2 flashlights. And if I'm not hitting that threshold energy, it doesn't matter how bright I make it, how many photons, as we now call it, are hitting the surface, no electrons are coming off. Actually, it's a threshold energy. More specifically, there's a threshold frequency of light. But if I exceed the threshold, then if I make it brighter, I get more electrons coming off of it. But if I'm below that threshold frequency, it doesn't matter how much I do, how bright it is, how much I hit it with, I can't get rid of the electrons. So that was a strike against the wave theory. Einstein figured this one out. This is one of the several things that he did for them to finally say, well, we can't deny him a Nobel Prize anymore. He deserved several. Instead, he got it for contributions. You know, the anti-Semitism of the time still boggles my mind, but Nazi Germany did not pop out of a vacuum. All right, so the other one was that if I take an atom with its electrons zipping around here, so I'm not dealing with a surface anymore, I want to be able to take a look at light coming in. So I have light coming in. It hits an electron and the electron goes shooting off. Well, some light also comes off of it as well. So light hits it, but the light that's coming off of it is not quite the same as the light that comes in with it. There's an energy loss when the light gets transferred to the electron, and then the light that's left over, the difference in the energy the electron has versus the energy the light had to start with, is reflected in a longer wavelength. or a smaller frequency. This is known as Compton scattering. And you actually can resolve this just with a simple conservation of momentum. If you think about light as being a particle with a certain amount of momentum, it's gonna hit it, you can do the calculations, you come out with the longer wavelength, which matches what we've seen. And then the last one I sort of want to mention with problems with classical mechanics. So I have my nucleus here. Which they'd only realized, so we're talking early 1900s when they finally figured out there was a nucleus. Actually, let me talk about the nucleus experiment. The model of the atom before this come out by J.J. Thomson, the guy who discovered electrons. And he had what is known as the plum pudding model. I don't think I've done a plum pudding model with this group. Okay. And the idea was that an atom was this, basically, there's a whole bunch of positive charge, something like a sea of positive charges. And then the electrons were like plums in pudding. So you have discrete electrons here, and then you've got this mess. If that is the case, if I take some foil, happen to be gold foil in the experiment, and I shoot alpha particle at it, so let's think about, what is an alpha particle?
It's a helium with no electrons.
Right, the helium nucleus. So this is 2 protons and 2 neutrons. Pretty sure it's 2 and 2, yeah, 2 and 2, typically. So we have this thing that's basically the mass of 4 protons being shot at this. Now, you got the soup here, which might slow it down some, but if it hits an electron, let's think about relative masses here. The mass of an electron is on the order of 10 to the negative 31st. Mass of a proton is on the order of 10 to the negative 27th. And I got 4 of these. What's going to happen when an alpha particle hits something that is roughly 1/10,000th of its mass?
Nothing. Pretty much nothing.
Oh, what's going to happen to the electron then?
You just get pushed along with it or pushed out of the way.
Yeah. And so what you would expect to see is, if that is true, I shoot alpha particles at this, I have a detector over here, or at this point, I have grad students looking through a viewfinder to see if it flashes when the electron hits. Or, I guess, when the alpha particle hits. And you basically look at it from that angle, and then you just slowly move it around at various angles here. And you would expect almost all of them to be basically in this narrow region. What they found is, not only did it spread out, but occasionally the alpha particles would bounce backwards. The classic analogy is to be like throwing a bowling ball at some tissue and having the bowling ball bounce backwards. So they did some math, they figured out that there has to be some hard nugget inside that would bounce the alpha particles off. Thus the nucleus. This is what Rutherford did. This is Rutherford. The one who said that all science is either physics or stamp collecting. And he won a Nobel Prize in chemistry, which is a strange tale in itself. He was actually nominated for a Nobel Prize in physics and chemistry for the exact same thing. But he wasn't going to get both for it. There was some wrangling back and forth over which one to give him for. He's had 5 of his grad students, 6 of his grad students go on to win Nobel Prizes in their own rights. He never got one in physics, which is a shame. He considered himself a physicist, thus the stamp collecting comment. All right, so I have an electron here, zipping around the nucleus. What can you tell me about an electron that moves in a circle?
Constant velocity.
Pardon?
Constant velocity, if it's in a circle.
Ooh, I would say quite not. Why is it not constant velocity if you're traveling in a circle?
Well, same magnitude, or same speed, I guess.
Ah,
is what I'm
okay.
thinking.
So we can go with the same speed. So if it's traveling at the same speed, but traveling in a circle, what can you say about it?
Constant radius.
Okay. In general, what do you say about anything that's traveling in a circle?
Orbit.
All these are correct words, but
Constant acceleration. Right.
constant magnitude of acceleration, given all the other stuff. But the key there is it's accelerating. So what comes with it? Let's think back to early on in the semester. What comes with an electron? Besides a negative charge.
An electric field,
Yep. Which way is that electric field pointing? Just
Towards it.
Which way?
in towards it.
Okay. So I have an electric field towards it. So as the electron's moving around and it's accelerating, that electric field is changing. What should happen? Now bringing stuff from a couple weeks ago.
You end up creating a magnetic field, or potential.
Not just a magnetic field. Other people can play too. In class, I did if I have an electron here and I move it back and forth.
A voltage, like an electric potential.
Yeah, it's still. Let's go to Maxwell's contributions. Let's see, Maxwell's equations, so we, the two Gauss's laws, then we've got